So now let's quickly do an example to prove that what we were saying is true. Okay, so example. Show that pair production cannot happen in empty space. Okay, so what was pair production? Incoming photon becomes electron and positron. So let's start with our conservation laws. The first one is conservation of charge. Is that going to be true? 0 equals 1 minus 1. That's good. So charge is conserved. Not a problem. Number 2, conservation of energy. That means energy before must equal energy after. What is the photon energy? Because it only has a photon. Suppose if it is HF, must equal 2 gamma mc squared. Because this is because there are 2 particles, electron and positron, and gamma is the relativistic factor. And mc squared is the rest mass. So that's not a problem. We know that that will be true. So not a big deal. Number 3, conservation of momentum. You know it's linear momentum, right? Not angular. I'm just going to call it momentum. Okay, that means momentum before must equal momentum after. So before we have photon, and after we have electron plus positron. Now remember, this is again going to be a 2-dimensional problem. Plus minus going this way. So along the x-axis, what will it become? HF over C equal P cosine theta plus P cosine theta. Because these are electrons and positrons, they are exactly equal, they have the same mass. Will they carry the same momentum and the same angle? Otherwise, conservation will not happen, right? So these angles, this angle right here and this angle right here must be identical. Otherwise, this will not work. That's intro 1. And along the y-axis, I will have 0 equal P sine theta minus P sine theta. So that one kind of goes away. Makes sense, right? So one goes down, just kind of goes away. So I'm just going to ignore this for now. Okay, so if I only look at this equation, may I rewrite this as HF equals 2pc cosine theta, where P is momentum? In the relativistic terms, may I write this as 2 gamma mvc cosine theta, where v is the speed of the electrons, c is coming from the speed of the photons. You see the difference between the two? This will be just HF. And why 2? Because there's 2 particles. This is the mass of the electron, this is the speed of the electron. So this comes from the electron positron pair. Oh, and gamma is a relativistic term. Anyone remember what gamma was? 1 over square root of 1 minus v squared over c squared. Okay, so what do we get? HF equal 2 gamma MVC cosine of theta. Now, is this statement true? V will be much, much less than C. Yes? Right, C is a photon. So no matter what the electron does, it will never be as large as C. And cosine of theta, through experimentation, they know that it's equal to 1 or less than 1. Right, from 0 to 1. This means that your 2 gamma MC squared will always be less than HF. But here, up here, that's what we said. 2 gamma MC squared equals HF. You see a contradiction in those statements? Both cannot be true. How do we make both true? The only way to make both true is that if you introduce an extra nucleus that takes care of this mess that the conservation of momentum is creating. So if part of that momentum, that photon energy or the photon momentum is being carried away by the nucleus, that's the only way to make these two statements be true. This cannot be false. Cannot be false. Or else our whole universe falls apart. What? No, energy has to be conserved. No matter what you do, the energy has to be conserved. Now, momentum, on the other hand, we can introduce other things to it so that the momentum is conserved. Okay? And the way we do that is to make sure that this statement holds false. So, how do we do that? We involve another nucleus to carry away the extra photon momentum. Because energy cannot be created and or destroyed. It has to be conserved. Otherwise, our whole universe is going to fall apart.